Hello, and welcome to this Control Engineering webcast focused on troubleshooting industrial networks, sponsored by Fluke. Now, here's why we're doing this webcast. Over the past 2 decades, industrial networks have grown dramatically from simple communication structures designed to send messages from controllers to machines and then back to the controller or HMI. But now these networks are entrusted not only to carry the mission-critical data they were initially designed for, but also to connect with enterprise software to exchange real-time production data, receive data from enterprise-level software, and even handle machine and process safety communications. Now, as the functional responsibilities of industrial networks have grown, so too has the roadway on which industrial communications travel. With 4 to 20 milliamp communications as a tried-and-true baseline and a still popular method of conducting industrial machinery, the manufacturing industries have seen the rapid rise of Ethernet and wireless technologies for industrial networking over the past decade. And as a result, many companies now have more than one type of network in operation, which only adds to the need for industrial networking engineering expertise. And that's why this webcast is focused on addressing the ins and outs of industrial networks, how they transfer data, how they're configured, and some basic troubleshooting diagnostics and techniques. I'm David Greenfield, Editorial Director of Control Engineering, and I'll be moderating this roundtable discussion featuring these experts from Fluke: Hilton Hammond, Product Marketing Specialist with Fluke, and Mara White, Marketing Manager with Fluke Networks. And the specific topics we'll be exploring today include the basic theory of industrial networks, how data are transferred from one point to another, and typical system configurations, the major problem factors, and here we'll consider the various environmental factors that have the most negative impact on network operation, key troubleshooting diagnostics and techniques with a specific look into general Ethernet troubleshooting, and we'll also take a brief look at the role of standards and how they govern the network protocols on which industrial networks are based. So, with all that said, let's start at the best place to start, with a good grounding on how these networks operate. So Hilton, we all know there are many different kinds of industrial networks, each with its own proprietary way of handling messages or interacting with devices. Can you explain how they all operate on a basic level?
David, thank you. Imagine when people meet socially or for business if the discussion is not conducted in an orderly manner. For example, everybody tries to talk over each other in a meeting room, or we all speak a different language. And one we have all encountered before, no doubt, a contractor next door pounding on a concrete slab with a jackhammer. Would we ever get anything accomplished? The key to successful network communications is adhering to the rules and protocol defined by industry standards. Standards are created and thoroughly tested to improve the efficiency and reliability of data communications. Data can be transferred through different means. In today's environments, we see analog and digital. If we talk about this in terms of end devices, this distinction is very clear. Analog I/O provides an analog voltage or current that is directly proportionate to the unknown input, making it possible for a controller to measure the voltage or current, then derive its value. For example, a level sensor might output a current 4 milliamp to 20 milliamp, where 4 milliamp might be the vessel is empty and 20 milliamp full. With digital devices, the unknown signal is converted to a binary code made up of ones and zeros. These binary bits are transmitted along with a common cable infrastructure. The advantage of binary information is you can now add addressing information, making it easier to communicate to one or more devices at a time.
So Hilton, now analog's been around forever, going all the way back to analog control loops formed by direct point-to-point connection from the controller to the end device. But how does the digital architecture differ?
Let's take a look. With the digital network, we can easily include addressing and routing information, making it possible to directly communicate over multiple network segments, or within multiple devices over a common cable or trunk, to form a controlled network of instruments and devices. At the lowest level, a typical FieldBus scheme connects devices to a communication trunk via a spur. typically the trunk is connected directly to a programmable controller. Often, the trunk also provides power to the end devices.
Thanks, Hilton. Now let's turn to Mara for a bit for this next question here. So Mara, looking beyond analog and digital FieldBus networks, can you explain how the function and application of Ethernet differs?
Ethernet is finding its way into all layers within the industrial network. Even some of the latest end devices, like variable speed motor drives, are now being controlled over an Ethernet point-to-point connection. When it comes to routing, addressing, and communications over multiple network subsegments, Ethernet is the predominant protocol being used. As the networks get larger with more and more communications over the backbone, Ethernet has advantages like speed and protocol routing management over traditional networks. At the next layer, multiple network trunks may in turn be connected together through switches or routers over a fiber or copper Ethernet backbone. Often the Ethernet network will bridge or connect multiple automation processes to a control room running critical applications. In some cases, the production processes are integrated into a company's back office network, passing critical production information for finance, operations, and reporting metrics.
Thanks, Mara. So now that we've got a clear picture of the overall architecture of FieldBus and Ethernet industrial networks and what you can do with the data, I want to ask Hilton a question here. Hilton, can you explain how the digital devices connected to these networks transmit and receive all this digital data over the networks?
Sure, David. Let's start at the lowest level, the device physical layer. The Open Systems Interconnect, or OSI initiative, divided the communication process into several distinct layers. Each layer created or managed a part of the process of taking a variable or string and encoded it to an electrical signal such that it can be transmitted on a copper, fiber, or wireless medium. For the most part, an industrial FieldBus device only utilizes the data link layer and the physical layer from the OSI. Looking at the right of the diagram there, starting from the top down, the device starts with the variable or word in the form of digital ones and zeros. The data link layer adds critical information such as addressing and or link control bits. This information essentially defines to which device to communicate to and establishes the communication dialog link, much like dialing a telephone number. Once the digital packet is created, the next step is to encode the packet of ones and zeros into an electrical signal and through specifically designed connectors and cables transmit the signal on a common medium. The receiving device essentially reverses this process. So here are two examples of digital communication protocols used in industry today. Firstly, the IEC 61158 Type 1 protocol. Through a sequence of messaging and handshaking, establishes a link to the receiving device, after which the information is exchanged. At the conclusion, messaging is exchanged to make sure the information received was error-free. Another protocol like that of ISO 1198 creates a larger packet of information that includes addressing, a checksum bit, and an acknowledge bit that is communicated to all devices on the network. Using this information, the intended receiver will pick the packet of data, use the additional data bits to check for errors and acknowledge receipt of the data. Every other device will ignore the packet. Since the packet error check occurs within the data transmission negotiation sequence or the specific bits within the packet, it's left up to the device to report the errors. Packet transmission errors are likely an indicator of physical layer problems.
So Hilton, once you have a packet of data in the form of ones and zeros, electrically, what constitutes a digital one and a zero?
There are many schemes used to translate a digital one or zero to an electrical signal. Manchester encoding is one of the more commonly used schemes. In this scheme, the signal transitions from one distinct voltage level to another is used to represent a logical 1 or 0. A low voltage often negative, to a high voltage represents a logical 0. The inverse represents a logical 1. David, now that we have an analog voltage that represents a digital 1 or 0, the next step is to physically transmit the analog signal across long distances from one device to another. In order to make the transmission robust, most industrial standard uses a two-wire differential scheme. In this method, the transmitter essentially duplicates the electrical signal, transmitting both signal on two conductors simultaneously. The second signal being the inverse of the other. At the receiver within the physical link layer interface, the second signal is electrically re-inverted back to its original state. These two signals are then electrically summed.
So what's the advantage of duplicating and inverting the signals?
The biggest advantage is to minimize interference from noise induced onto the cables. Any noise induced on the cables will be induced on both conductors. Within the receiver, the physical link layer inverts, then electrically sums the two signals, canceling out the noise.
Are there any disadvantages to this?
There are not really any disadvantages, David, but one point that must be considered is the two signal paths must be electrically balanced. Any impedance difference between the two conducting paths can create potential errors.
I understand. Okay, now Hilton, I just want to back up for a second. Earlier in the webcast, you mentioned that standards exist to govern network communications. Can you give us an example of one of the more critical specifications that can influence the performance of a new or an existing network installation?
David, yes. This is also a great way to understand what, where, and how to test an existing trunk or spur to ensure it is operating optimally. Using the standard as a reference can point you to potential weak points and even isolate a problem down to a component. Network standards cover a wide range of subjects and are very detailed and often extremely complex, therefore impossible to cover every point in this short session. However, the physical layer portion of the standards can be broken down into three critical areas, those namely being 1, network topology, 2, physical layer signaling characteristics, and lastly, the network medium. Using the IEC 61158 Type 1 as an example, we can go through some of these critical specifications. First, the standard defines the network topology, defining the number of devices, the architecture, how they are connected together, and key characteristics like maximum length. Next, to ensure the encoded signals are transmitted from point A to B correctly, the standard will typically define key electrical characteristics of the encoded signal must conform to. Often the specifications are divided into the signal's amplitude and time domain, plus signal quality characteristics like noise rejection, distortion, and jitter. Lastly, the standard will define the cable medium and the connectors. A more recent innovation is the M12 connector, designed to offer better resistance to the environmental ailments like dust and moisture found in today's industrial plants.
Thanks for clarifying that, Hilton. So, Mara, let's get back to you for a bit here. Since we're on the topic of standards, can you explain how the Telecommunications Industry Association specifications address the industrial networking space specifically?
Sure. Otherwise known as the TIA, the Telecommunications Industry Association provides standards that govern both design and installation practices for data communications. The TIA defines two key tests no matter the networking space, the channel or permanent link test. When a new cabling system is installed, the installation crew is typically not responsible for the patch cord or equipment cords outside of the walls. This crew pulls the cables, labels, terminates them, and certifies the performance of the permanent link, or portion of the installed cabling that's part of the permanent infrastructure in the building. The channel test, on the other hand, includes all of the permanent link plus the patch cables, and is often used to verify end-to-end data performance. The channel measurement is much more applicable to the industrial networking space. Also, the TIA has an addendum for the industrial premises. This is the TIA 1005. and this introduces the M12 connector and permits up to 6 connectors of either RJ45 or M12 within each channel. The addition of 2 more connectors will inevitably reduce the performance of the overall link. When this topology is used, the channel test becomes critical. And with more connections, the grade of the components like cabling, connectors, and patch cables used are even more important. Now just to clarify, the M12 connector is an IP-rated 67 connector that has the transmission requirements of a Cat5e RJ45, but is a 2-pair connector specifically designed for use in the harshest of environments.
Thanks, Mara. So now let's look at the factors that can impede network performance. So let's stay with you, Mara, here for a bit. What are the predominant factors that have the most impact on industrial networks?
Industrial plants are often harsh, dirty places, both electrically and environmentally. The big difference between an office environment and an industrial plant is the office is designed for our human comfort and safety, thereby reducing the potential impact to sensitive low-voltage electronics. The industrial plant can pose significant challenges to sensitive low-voltage infrastructure and electronic equipment. The first factor is heavy-duty, high-voltage equipment inducing EMI. The second factor is a factory or plant floor has exposure to the elements and operating equipment where temperature and humidity are often not controlled. And thirdly, the installation environment is often to the extremes where common processes can create steam and condensation or are required to withstand direct contact with water. Then the equipment itself, like the fans and conveyor belts and presses, create continuous vibrations. All of these factors stress sensitive electronic equipment and data infrastructure to its maximum.
So can you give us a few examples of the problems a harsh environment creates for the networks?
Sure. For example, we have seen at specific customer sites problems in a variety of different environments. We've seen water intrusion from shift change washdowns. We've seen extreme freezing temperatures in a frozen food plant affecting components over just a short period of time. And, on the other end, extreme heat and condensation in a food and beverage cleaning in place process, causing corrosion on all the connections. We've also run into overlong cabling runs at a wastewater treatment plant in order to support applications at opposite ends of the plant. And excessive ringing introduced by a short cabling run between equipment installed in a control cabinet that created an impedance mismatch. So the end-shielded twisted pair copper cabling can be damaged by both prolonged sunlight and freezing temps. The electromagnetic interference, or EMI, generated by electrical equipment causes noise that impedes network traffic. And corroded connections of any type creates performance issues. So as a general rule, as distances increase, so must the grade of cabling. Conversely, as the data rates increase, the distances must be kept within a strict limits, no matter your industrial setting. All of these factors need to be considered when selecting industrial Ethernet cabling component, or it may fail in the field.
Thanks, Mara. So now that we've looked at the network standards, the environment the networks operate in, and some of the typical problems, how would an engineer go about troubleshooting the network?
David, we get this question often, and in order to better understand the process, it's simpler to break down the network into its core elements. Using the diagram, following the flow of control data from left to right, the core elements are the Ethernet communication protocol between the server and the switches, the Ethernet infrastructure over the Cat5e fiber or wireless, and then down to the FieldBus cabling infrastructure, like twisted pair or standard AWG, and then the FieldBus physical layer electrical signaling. Performing critical measurements to understand if the components meet the specific parameters or characteristics defined by the standard can help diagnose a problem to a specific location or component. And if you're deploying a new installation, these measurements can provide a baseline report on the status of the installation as well as a relative reference to compare against down the road if something becomes intermittent or goes mysteriously wrong.
So, without going into too much detail, Mara, can you give us some further examples of the critical measurements needed in order to validate the performance of a network?
Absolutely. As we look on the left-hand side, we see the Ethernet communication protocol. And the measurements that are going to be important at this point are going to be switch port configuration issues, things like authentication or VLAN validation. We also have traffic statistics and understanding the utilization of any of the communication. Also an opportunity to highlight transmission, alarms, and errors. We're also looking for packet routing and addressing issues, or latency and throughput, anything that can be attributed to the signals passing between the servers and the switches. As we move to the right, the Ethernet medium highlights the physical infrastructure, like the Cat5e or fiber. Here we're looking for length and opens and checking the wire map. So we're identifying the wiring errors such as shorts between any two or more conductors, or an open circuit or break in the cable. We're looking for any reversed wire pairs, split pairs, or transposed pairs. Also looking for the attenuation level, or the loss of signal over the distance. And also taking a look at crosstalk, where we're identifying if any individual pairs on a cabling signal are affecting the data signal. As we move into the FieldBus medium, the critical measurements here surround the physical characteristics of the cable. Parameters such as connectors, opens, shorts, cabling length, and opens and shorts, or measurements of impedance, capacitance, and grounding connections are important. And then at the far right, on the FieldBus signaling level, it is the integrity and quality of the signal that we're measuring. And measurements such as amplitude and device supply level, noise, and distortion can all affect the overall quality. So if we look at an Ethernet protocol example, being able to see into your network is something that is intangible and is an invaluable time saver when troubleshooting. So if we look at an example with an Ethernet protocol, say you have a managed switch with one IP address and you have an end device like an Ethernet-enabled I/O, like a sensor on a packaging line on the other end, and the sensor is reading slower than it was yesterday. You can sit down at your PC and dive down and sift through each switch and switch port to review the traffic at each end, or you can pull out an instrument like an Etherscope and connect anywhere on the network and see immediately what kind of traffic is transmitting between those two devices. The Etherscope allows you to see if both ends are transmitting at the same speed and duplex level, and give you protocol details on that transmission. If not, then you can go change, if they're not at the same level, then you can go and change the configuration of the switch to auto negotiation, or hard code them to the lowest common speed as long as they're the same at each end. This option is an excellent first step over spending time diving into the switch or jumping to conclusions that you have an equipment failure and acting on replacing a sensor when that may actually not be needed. On the Ethernet medium side, in this example, we're looking at the DTX cable analyzer. And this is used to determine whether water has entered a cable and where. On these screenshots, we're taking a look at the return loss, and that the return loss has failed significantly looking at those graphs. There are two classic indicators of a cabling issue and water being present. As a rule, if the link fails at the lower frequencies, it's a physical cabling issue. When all four pairs fail, and they're almost identical in nature, then you can surmise that water is present. We can use a high-definition time-domain reflectometer to locate where the water has penetrated the cable. In this case, water has entered the last 2 meters of the conduit at the floor box, and the cable analyzer shows this clearly. The same TDR-type functionality can be used over fiber with an OTDR. Over fiber, the result is a signal loss over distance graphical representation called a trace. This is a single-ended test, so you're not required to know where the other end of the fiber is to get an idea of where a problem may be. Any reflections are recorded as reflective events and seen as spikes on the screen. OTDR traces provide performance details about the connectors, splices, or breaks along the fiber optic link. And this is true for any OTDR.
Thanks, Mara. So now, Hilton, let's turn things back to you for a bit. Mara gave us some great Ethernet examples. Can you give us a FieldBus cable example?
David, yes. Essentially, the goal of testing a FieldBus cable is to check for opens and shorts between the electrical signal conducting paths, making sure we test each cable pair combination. Also, for testing purposes, we should think of the copper wire as a source of impedance, measuring the cable resistance of each conductor, as well as the resistance and capacitance between them will help us understand the cable impedance. Any impedance mismatch across the transmission path can potentially degrade the encoded signal.
Now, Hilton, just for a second here, I noticed in your slide that you suggest using a digital multimeter. Why would you use that instead of a network cable analyzer?
David, that's a good question. A cable analyzer is designed to test a very specific cable type to a well-defined industry standard parameters. For example, those parameters like crosstalk, impedance, and attenuation defined, for example, in the TIA Cat5e specification. Often industrial field buses, we use standard common electrical AWG grade 2, 4, or 8 pair cables. These are untwisted or twisted cables with no set of special measurement standards are yet to be defined. Unfortunately, to date, the industry has yet to define a common standard. Therefore, at a minimum, we must use a digital multimeter to test the basic characteristics like resistance and capacitance.
So since the integrity of the encoded signals is obviously very important, can you provide an example of what might degrade the analog signals?
Yes, the quality of the electrical signal can sometimes degrade to the point the receiving device can no longer distinguish between a digital 1 or 0. The first example on the left-hand side shows a Profibus network where one of the devices connected on the network was not properly grounded. This created a common mode signal on the digital line. The second example on the right-hand side shows the impact of an impedance mismatch in the transmission path. An impedance mismatch can create a reflection in the waveform. Excessively high or long duration of reflections can potentially confuse the receiver to misinterpret a logical 1 or 0.
Well, looking at those waveforms, I can see that trying to analyze them to determine if there's any problems could be really overwhelming, especially if you don't know the standards inside and out.
Exactly. That's where a tool like an oscilloscope with built-in automatic measurements that are compared to the industry standard can make the task not only possible, but fairly straightforward. Here we measure the critical parameters of a waveform characteristics defined by the standard, usually in the domain of amplitude, time, and signal quality, so we can attribute the problem to one of those areas, making it possible to narrow down the list of potential root causes.
So thanks, Hilton. Well, we've covered a lot of networking material here today. So Mara and Hilton, what would you say are the key takeaways from this discussion about network problems and how to troubleshoot them?
In summary, in an industrial network, there are 3 areas where problems can occur and affect network performance. If any one does not work, the entire network segment will fail. When troubleshooting these problems, focus on 3 areas: the network, electrical signaling, and cabling infrastructure, no matter the medium. This can be completed with tried and tested test and measurement tools.
So thank you, Mara, and thank you, Hilton, and everyone who has joined us for this webcast. As a viewer, I hope you come away from this webcast with a definitely more solid grounding in the technology and troubleshooting techniques of industrial networks. Now, if you have any questions, please forward them to me at david.greenfield@readbusiness.com, and I'll make sure the panelists get them. And also, please visit the website of our panel participants to learn more about their specific offerings on the topics we discussed here today. And if you have ideas for other educational webcasts you'd like to see Control Engineering present, please drop me a line at the email address shown. Thanks for tuning in.